This is an example that shows that we have to be a little bit careful when we apply Green's theorem. So it asks us to do two things. First, to show that the curl of this vector field is 0, and then to do a line integral, and then kind of explain what's going on about Stokes' theorem in this case. So the first thing they ask us to do is to find the curl of this vector field. So we're going to find the curl of our vector field f. So just remember it as ijk, d dx, d dy, d dz. We put in our functions minus y, x squared plus y squared, and x over x squared plus y squared, and z here. So first, the I component, we have the derivative with respect to y of z, which is 0, minus the derivative with respect to z of this function that doesn't involve z, so that's 0. And then for j, we have the derivative with respect to z of this function that doesn't involve z, so that derivative is 0, minus the derivative with respect to x of z, which is also 0. So the first two components are 0. Now, to get this last component, we need to take the derivative with respect to x of x over x squared plus y squared. Let's do that. To take the derivative with respect to x of x over x squared plus y squared, we can just use the quotient rule, which says you take the derivative of the top times the bottom minus the top, which is x, times the derivative of the bottom, which is 2x, all over the bottom squared. So x squared plus y squared squared. So we end up with, we have an x squared and a y squared and a minus 2x squared. So we end up with y squared minus x squared over x squared plus y squared squared. For the other component, we have to take the derivative with respect to y of minus y over x squared plus y squared. You can see that this is going to be, because of the symmetry in these two problems, we're taking the derivative with respect to x, we've got x and x squared here, whereas here we have y, and y squared there. So because of the symmetry, this is just going to be, there's an extra negative sign, but it's going to be a negative in front of, let's see, x squared minus y squared all over x squared plus y squared squared. Now, to get the curl, we have to take this one and subtract this one, which subtracting this negative would be the same as adding them, and you can see that this one's got y squared, and that one's got a minus y squared, so those cancel. This one has minus x squared, and that one has plus x squared, so we end up getting 0 for the result there. So sure enough, the curl of f is equal to the 0 vector. So it's 0 all along, because we could use a bold 0 to indicate that it's the 0 vector. Now let's do this circulation integral. We have the circle of radius 1 in the xy plane, so we've got this, we're in 3 dimensions, but we've got the circle of radius 1 in the xy plane. So let's just set that up. Our parameterization, it's a curve, right, and we need to go around that. It doesn't matter which way we go. I guess I could use this parameterization. I could do cosine t, sine t, and then the z-coordinate's always 0 for t between 0 and 2 pi. So we can set up that integral. We've got to go from 0 to 2 pi. We've got to do f dot t ds ends up being integrating f dot r prime of t dt. So my vector field f, in terms of my parameterization, see, x squared plus y squared is 1, and so we have minus sine t over 1, right? And x over, this is 1, our parameterization, and x is cosine t, so we get plus cosine t. And then z, but on this circle, z is always 0. So there's my vector field. I need to dot it with r prime, which is minus sine t and cosine t and 0, and then integrate dt, which gives me the integral from 0 to 2 pi of, see, negative sine times negative sine would make sine squared plus cosine squared plus 0. Sine squared plus cosine squared is 1, so we get the integral of 1 dt, which is equal to 2 pi. And that's kind of the conflict in this problem. See, the issue is Stokes' theorem says if I integrate around some curve, f dot t ds, so I found the circulation around the curve, that ought to be the boundary around the interior of the integral around the interior of that region, right, or the surface that this is the boundary curve for. You could use any surface, but say that circle in the plane, of the curl, so del cross f dot n d sigma. But we just showed that the curl of f is 0, so if you go around any surface, I should say this should be some surface r in general. If you go around any surface, then you're integrating up 0, you'd have to get 0, but we just found that the circulation integral was 2 pi, so what gives here? Well, we weren't very careful when we did this, because no matter what surface we're talking about, you could use a circle in the plane, but any surface that this is the boundary for would have to contain, at some point, the z-axis. Now, on the z-axis, x squared plus y squared is not defined, and so the curl, well, actually just the vector field, right, is not defined. This is undefined, so f is undefined on the z-axis. If f isn't defined, then none of the partial derivatives of f are going to be defined, right? Because you have to be defined. You have to be defined in order for the derivatives to exist. So actually, the curl doesn't even exist on the x-axis. We kind of ignored that problem. It just so happened that if we didn't think about it, then we would get anywhere that we could actually write this down, and it made sense. We were getting 0 minus 0, but we had this big place where the curl wasn't defined. So that's the issue about using these theorems, is you change an integral around the boundary for an integral over the interior. Well, the integral around the boundary might be nice and defined, right? The vector field is defined everywhere here, but the curl is not defined everywhere in the interior. You have to do an integral around the interior. So just be careful. Make sure that your vector field is actually defined and that you really do have a curl as you go around that interior before you do it, because you might make a mistake and say that the circulation is 0 when Stokes' theorem really couldn't be applied because you didn't have a curl throughout every point in the interior.